Okay, let's go ahead and get started. So what the plan was today is to go over homework 2, module 2, and that's what I was going to do, go over this in class and post it online for anyone that either taking the class online or if you have any questions about how to solve it, go over that. It's pretty straightforward. So let's go over this first, and then if anybody has any questions about the material for Module 2, I'll go over that. Okay. So basically what we have is we want to solve the following linear programming model graphically. So what I'm going to do is just come down here and snip this and put this in Note, and then that way I can view it. And go ahead and snip this graph. Okay, so basically what we have is we want to solve this maximization problem. It's a linear programming model. The way we know it's linear programming is if you look at basically all the exponents in either the objective function or either one of the constraints, you see that there's no exponent greater than 1. So it's just a simple linear programming model. So we want to take this function right here, which is our objective function. It's in terms of x1 and x2, and we want to maximize or get the maximum value we can based on having these 4 constraints. And a lot of times these 2 constraints here, this is what we refer to just as non-negativity constraints. And basically what they're meaning is to say that we want everything to be greater than both our x and y axis. So they kind of constrain us to the x and y axis. You don't have to have them, but many times in real world problems you'll see this because you can't have a negative quantity. So the first thing that we're going to do is we're going to draw the constraints. All right. So over here I have these constraints that are drawn, and you know, if you look at this line right here, this goes to the constraint 4x1 plus, I'll just say x2, I'm going to say is equal to 16, because if it's greater than, it's going to be a region, but if it's equal to, it's actually equal. So this is going to be the boundary of that constraint. So if you remember, really, you know, x1 is equal to x, and x2 is equivalent to y in terms of our x, y axis. You can actually call them the x1 and x2 axes. I mean, there's absolutely nothing wrong with that, but just in standard notation, we're kind of used to the x, y axis. So, you know, you probably remember seeing something like y equals mx plus b, you know, from your algebra class. So what we're going to do is we're going to then rewrite this equation to be in terms of x2. So x2 will then be equal to 16 minus 4x1, and then we can divide this out, and that'll be what, 4, let's see, mx plus, actually that's okay. We can just rewrite this as negative 4x1 plus 16. Right? So do you see how this is written in the what's called the y-intercept notation? I think that's what it's called. As to x2 is equal to negative 4x1 plus 16. That's essentially equal to y equals mx plus b. So what would be the slope of that line then? So the slope of this line is equal to what? It's going to be negative 4. And then your y-intercept is equal to what? 16. And so do you see how we were able to draw this equation right here equates to that line. Does everyone see that? Okay. And so then this equation right here is going to be this line. All right. So what I'm trying to show you is just, and you probably already know how to do this, but I'm just trying to show you how you take those equations and you turn them into just two lines. Okay. And so because we have these inequalities here, this less than means that we're looking at all points less than this line. So essentially, we're going to be searching now this region here, and these two mean that everything has to be above x, or above 0, above y. So we're essentially searching this region right here for the point. Then when we pick a point in this region, and we just pick some random point and plug it back in to this equation right here, that value is going to be maximized. Okay? And the analogy that's in the book and that I've used in the lectures is, like I said, you kind of think of this region here as being on the side of a hill, and you've got two fences intersecting, and you want to go to the point inside of that boundary such that your elevation is maximized. So that's kind of a real easy analogy to think about. I mean, just drive out towards Tazewell. That's where I like to go for this mental example, and start looking at some of the rolling hills and up on the side of the mountain, you know, these big fields, and imagine that you have a fence that fences in a boundary that looks something like this, and it's just laid out, you know, this quadrilateral is laid out, some irregular four-sided polygon is laid out on the side of the mountain. It's cleared off, and you buy that, and you want to go figure out where the maximum elevation is. Okay? Well, probably if it's completely flat, the maximum elevation is not going to be on the interior. Okay? If it's curved, it can be, but if it's flat, it's not going to be on the interior. It's going to be on one of these corner points. Okay? So then what we have to do is we have to figure out then where each one of these corner points are. All right? So let me make another page and grab this guy right here. Put it in. And let me go ahead and get these equations. Let me just grab everything again. Probably the easiest thing to do. Okay. So now all we're going to do is we have to determine these four corner points. Well, this guy right here is easy to figure out. Well, what's the coordinates? It's going to be 0, 0, right? So that one is very easy to figure out. Now we need to figure out this coordinate, and we need to figure out this coordinate. Okay, well, the way we would figure out those coordinates is we would just simply set these equations. We would figure out where the y and the x intercept are. Okay, so we just use standard algebra, and so that one's those are real easy to figure out. So this one right here is going to be at 4, 0 right here. This one's at 0, 6. So 3 of these 4 points are relatively easy to figure out. Okay, it's just where the lines cross either y equals 0 or x equals 0. This fourth point is by no means hard, but that's the one where we kind of have to go in and figure it out using some method. So how do we go about doing this? Well, we have two equations, 2x 1 plus 3x2 is equal to 18. 4x1 plus x2 is equal to 16. So now we want to solve for x1 and x2. And how do we go about doing that? Anyone remember how to do that? multiply and subtract out, substitution. There's a couple ways. So what I'm going to do is just take this guy right here and multiply times -3. Okay? So then this will give me negative 12x1 minus 3x2 equals what? Negative 48. All right? Now I'm going to take this guy right here and add it to this guy right here. So I get what? Negative 10x1 plus 3 minus 3 is going to be plus 0x2 is equal to negative 30 divided by negative 10, negative 10. So I get x1 is equal to 3, right? That gives me this value of 3. Then, to find what the value of x2 is equal to, I just plug in a value of 3 in either one of these equations. So 2 times 3 is 6. 18 minus 6 is 12. 3x2 is equal to 12 divided by 3 divided by 3. x2 is equal to 4. Okay, so that is where this solution comes from. It's just setting those two equations equal to one another, right? So we have all 4 points. Now what we're going to do is we're simply going to plug in those 4 points into our objective function and just evaluate what the value is. So if you plug in 0, you get a 0. If you plug in 4, 0, you get 8. If you plug in 0, 6, you get 18. And if you plug in 3, 4, you also get 18. Okay? So I created this problem by design to give you this. So it looks like, well, we have 2 solutions, okay, which is actually what we have. We have something, we actually have more than 2 solutions. What this is telling us, when we look at this, is it's telling us that this guy right here gives a value of 18, and this guy right here gives a value of 18. Okay? So this objective function that is a projection, if you've watched that video, how I show that projection moves up and down over the boundary, turns out that in this particular case, and this is a very unique case, what you'll notice is that this equation right here, if you go in and you calculate the slope of that equation, remember how to calculate the slope of that equation? It's going to be 3 over 2, which gives you, actually it's going to be negative 3 over 2. Negative 1.5 has the same coefficients as one of these constraints, that constraint right there. See how the coefficients in front of x1 and x2 are both 2 and 3? Because of that, this tells us that the slope of our objective function has the same slope as one of our constraints. So the polytope, which is this guy right here, this quadrilateral, that objective function doesn't touch the polytope at one point. It touches it or intersects it at a boundary. So that means we have an infinite number of solutions to this particular problem. So as long as you pick a point on this boundary, you're going to get a value of 18. So I went in and just randomly picked another point. You know, I said, let's suppose we pick 2 and 14 over 3, which are 2 points on that boundary, and you plug them in to the original equation. Here you get 8. Here you, not 8, you get 4, I'm sorry. you get 4. Here you get 14. 14 plus 4 is equal to 18. So do you see how the optimal solution now has many more solutions than just one? Okay. Now, the reason why I always like to show this example is because later on in the course, we're going to get into other problems similar to this, maybe even integer programming problems that have what's called multiple optimal solutions, and then you're tasked with finding the best of the best, okay? And that's what's referred to as a secondary objective function. So I always like to show this to kind of show how this thing can work out. I don't know if it's best for this to be problem 1. Maybe I should have like problem 3. But regardless, everyone understand why this has multiple optimal solutions? Okay. Well, now let's go in and let's take a look at problem 2. And problem 2 is very similar to problem 1. They all basically have the same structure. I'm just trying to demonstrate something with these problems. So in problem 2, notice how these constraints here are identical to the constraints in problem 1. But look what happened to our coefficients in our objective function. I simply reversed them. It was 2 and 3. Now it is 3 and 2. So the impact that this is going to have, all right, we're still going to solve the problem in the exact same manner. Nothing actually changed in terms of getting these 4 corner points. So 0, 0, 4, 0, 0, 6, 3, 4. I don't have to go in and resolve those. I've already done that. Okay. The only thing that changes is the equation that I sub them into. Now, instead of subbing them into 2x1 plus 3x2, I'm substituting them into 3x1 plus 2x2, and I get different values here they're evaluated at. And so I find now that 3, 4 gives me the highest value. So if I go down here and I look, this stays exactly the same. Nothing has changed. But now 3, 4 gives me the maximum value, gives me a value of 17. And look how this objective function, the slope of this objective function changed. Okay? So let me snip this so I can draw on it. Yeah, I'll put it here. That way I can compare them side by side. Oops. Let's see, does it allow me to, I don't know if it lets me pick it up now or not. I moved it to the wrong place. It doesn't let me do undo, undo, undo. Yeah, there we go. I'll make it a little smaller. Okay, yeah. So do you see how these are exactly the same, these two graphs, except for this objective function? So do you see how the slope of this objective function was kind of rotated this way when we go over here? So essentially all we did was rotate that objective function slightly. Before we had, what equation did we have? We had 3x plus 2 y. So here, is that right? We had 2x1 plus 3x2. Here we have 3x1 plus 2x2. Okay? And a minute ago I told you wrong. This doesn't have a slope of 1.5. It has a slope of negative 2/3. I always get those confused. This one has a slope of negative 3/2. All right? I can never remember which one you divide out by the other. You look it up if you don't remember. It's no big deal. Okay, so do you see how this slope now is actually steeper than this slope? So that's why this is a negative 1.5. It's actually steeper in the negative direction. Does that make sense? So what happens is, where this guy right here had laid down on one of those constraints, one of those boundaries perfectly, now as you rotate this guy around like this, essentially it's only going to be touching in one spot. Okay? And the point where this objective function, or the projection of the objective function, just touches the boundary is going to be that maximum value. Okay? Does that make sense? All right. Now let's go down. And I think this will all kind of come together when I go through all four of these. That's why I made a variant of all of these. So everything's exactly the same in this problem except this objective function has changed. All right? So when we go in now and evaluate these 4 points for this objective function, now see how 0, 6 has the greatest value? So 0, 6 is this point right here. And if we go in and we look at the slope now, the slope of this guy is going to be what is that going to be? That's going to be negative 1/5. Is that right? That doesn't seem right. 15 over, seems like it'd be 5. But anyway, this is the new objective function right here. And you see how this objective function just touches the polytope now at this point right here. Does that make sense? And then when I go and look at the last one here, now we can see how the objective function touches the polytope right here. Okay? So if we were to evaluate using this function here and plug in these values, now the optimal solution is going to be at 4, 0, which is right here. Okay? So here's what I want you to think about. Let me go in and snip this. Wish there was a way for me to actually have a line and rotate it, but I don't know of an easy way. So what happens is, imagine you know, just having an objective function that you're bringing down. And as it moves down, this projection moves down, say it touches right here. Okay? So if this objective function was perfectly flat, it's going to touch right here. But imagine that as you change the slope, so I'm going to say you change m, and you rotate m like this. You make it more negative. All right. What's going to happen is, as this starts to change, look like this, that there's going to be a region, a certain interval of slopes where this remains the optimal value. And then there's going to be some magic slope, and that magic slope is going to be the exact same slope to one of the boundaries, where then it's going to touch in multiple places. So literally, imagine me taking this pen and putting it on the side of the computer, okay? And as I rotate, you see how it just stays at one point. Then I get to a point where this pen now is flat on the top of the computer here. And if I had a much longer pen or stick, and then if I rotate just a little bit more, See how the new pivot point becomes now this point right here? And that's exactly what's happening. That imagine you're taking this, say, a big long line right here, and you rotate around this polytope. This point right here becomes the pivot point. Then at some point, this will become the pivot point. And then this continues to rotate like this, and then this would become the pivot point. And then if you just kept going, this would still remain the pivot point. And then at some point, if you rotated enough, this would become the new pivot point. And then kept rotating, this would become the pivot point again. So imagine taking this stick and just rotating around the polytope. There are certain values of m, certain intervals, where the solution is a pivot point. And then there are 4 unique slopes, and it's real easy to figure out what those slopes are. It's the slope of this, the slope of this, like I said, the slope of this, the slope of this, and the slope of this. There are 4 unique slopes where you have an infinite number of solution, and then it moves on to the next corner point. Does that make sense? Okay. So why did I give you this example? Well, the reason why I gave you this example is because I wanted you to develop some understanding of actually what's going on in solving these problems. Because we're never going to solve another problem like this again. It's not like you're going to come in and ever have a problem, I'm not going to say ever, but probably very rarely, graph these and solve them graphically. Once you get into 3 dimensions, it's doable, but it's very, very hard because now you're dealing with rotating planes in 3 dimensions. And there's a point where a plane intersects what's called a facet of that polytope, and you have an infinite number of solutions. But then you could rotate in the xy, the yz, or xz direction. So it's just something. I do an example, a 3D example in the book. I kind of give some insights. So then once you get into 4 or 5 and higher dimensions, you lose all intuition graphically. So that's why we stick to 2-dimensional examples. So does everyone kind of understand the concept of what's going on with these problems? You get at least we're trying to maximize the value, right? And that there's some point where that value is maximized, or there's some points if the objective function is equal to the slope of one of the constraints. All right. Now, does anybody understand what these are? I didn't know I could write in there. So I've talked about those projections, like everyone understood what they actually are. But can anyone explain to me what these red lines really are? Well, why do we have multiple ones? If you can't, that's fine.
Really values if you plugged in that formula that would graph?
Yeah, so it's very similar to that. So let's go up here and, like I said, let me grab this, because this is an important point that I think a lot of times you just kind of nod your head, yeah. I get what's going on. And then when you actually go back and think about it, you're like, you know what, I really don't understand. Why do we have multiple red lines here? Okay. Well, the reason why we have 4 red lines is because those are 4 lines that I decided to pick. But here's what I want you to think about. Z is equal to 3x1 plus 2x2. Okay? So, depending on the values that I plug in for x1 and x2, does everyone agree that z changes? okay? I mean, turns out Z changes, obviously. But let's suppose that I make Z a constant, and I say, I want Z to be 18. And then I'm going to say 3 times this plus 2 times this. What values do x1 and x2 have to be such that Z is equal to 18? Do you know what values it has to be? Turns out there's an infinite number of values that you can get 18 from this equation right here. The problem is when you increase x1, you got to decrease x2. And it turns out that if you were to plot all of those points, you get one of these lines. All right? So let's suppose instead of having this be 18, I say I want to make it 14. Well, guess what? By reducing this value from 18 down to 14, now I may be dealing with this line. If I go down to like 10, it may be this line. If I go down to like, say, 6, it may be this line. So there's an infinite number of these red lines that I can have, but what they represent is the objective function, the value of that objective function evaluated at any point on these lines. And these are called isolines, okay? ISO meaning same lines, isolines. So just like in a, you ever watch the 6 o'clock news, and you've got like, say, the state of West Virginia kind of looks like this, kind of comes down, something like that, and they're showing weather, okay, and they show something that looks like this. They show something like that. Well, what could this represent? Well, this could represent temperature, could represent pressure, could represent, well, snowfall. I mean, if you wanted to do that. But what do these lines represent? They represent the point, all the points on this line show all the locations that say that have the same temperature. So if it has the same temperature, it's called an isotherm. If it has the same pressure, it's called an isobar. Same snowfall, I don't know what it's called. And those of you, if any of you that's in civil or taking any civil courses, these are what we call in map contour lines. And contour lines represent the same elevation. So when you see these right here, and I call these isolines, what these represent is the same value in the objective function. They're like saying elevation. And because we're dealing with linear functions, it's just like holding a piece of paper up. Say I hold this keyboard up or a piece of paper in the classroom, and I say, draw a point or all the points on this piece of paper or on this, say, mouse pad, that have the same elevation. Okay? Well, if we were to do that, you see how it's going to be a line. So if that's say a meter above the ground, it's going to be here, say 36 inches. And then if I go to 38 inches, it's going to be here. 34 inches is going to be here. So what these red lines are like projections. It's like in three-dimensional space, I have this flat plane, but if I wanted to try to project that on the XY plane, I would actually project. It's a projection, like this was transparent, and I had lines drawn on it with a thick marker, and I were to shine a light down, do you see how it would project that down on the ground? Now, if this is flat, but what would happen if I did something like this? And I said, pick all the points that have the same elevation. You see how it's not going to be a straight line. It's going to be some weird contour shape, just like I showed you with the map of West Virginia. So it turns out that linear programming is very, very powerful. So anytime that we can make a function linear, we try to. Even if it's not, if we can approximate it, the reason why is because you can literally solve these problems into the millions of variables. Okay? Now, we may not do it on this computer, but these are very, very efficient techniques. So imagine that you have something that you are trying to minimize or maximize, then instead of just having, x1 and x2 and x3 all the way down to x10, that you've got x1, x2, x3 all the way down to x2, the 252,000. You can solve it. And you can solve it on a machine, basically, that's not any more powerful than this machine here. You may have to have specialized software, but you can actually do that. And this becomes very, very powerful because you can get the absolute best answer across all of these decision variables. All right? So that's why OR is so important. All right? Now, if we're not dealing with linear, it becomes a little more complicated, and we're going to talk about that throughout the class. So that's why you have to go through and make sure that these functions are linear, or at least you kind of quasi-assume they're linear. Say, well, it's probably going to be close enough. Maybe the relationship, actually looks something like this, but you say, you know what, a linear line is close enough. We'll get a near optimal solution and then deal with that minor difference. Okay. Are there any questions on the homework? Did everything I do make sense? So this is just a very kind of low-level, not real-world example. These are just functions that I've made up to prove a point, but I want you to understand what is fundamentally going on graphically with these models. So then when we extend this to the next topic, notice the simplex method, we're doing that to get out of 2 and 3 variables to be able to go to n variables and abstract what's going on graphically to then define an analogy what's going on algebraically. All right? And then once you go to algebra, at that point, you can turn the computer loose on it, because then you start dealing with matrices and inverses and everything, and that's how it actually solves these problems. Because if you think about solving these simultaneous solutions, you can also solve this using matrices. Remember, you take like your matrix A here, and then you multiply times going to be this matrix, something like this. And that's going to give another matrix B. So then if you want to solve, this looks like, what is it, going to be A inverse 1B, something like that. Which, don't worry about it, but I'm saying that's another way to solve it. Well, this is prime time for a computer. At that point, it can just, just grind through those. And so that's why the computer is so powerful. All right. Any questions on the homework? Okay.